Welcome everyone. My name's Stephen Brooks and I've created the electrical protection course. Electrical protection is a key element in all electrical systems and ensures that the electrical network can operate safely and efficiently. We will begin by showing you the symbols that we use in protection schemes and introduce you to some of the protection equipments that you will come across and show how they all fit together. We will then look at some of the fundamental principles behind protection systems and show what we are aiming to achieve when we put these systems together. Next, we will look at three-phase currents and show what a healthy electrical system looks like and how we can break down the AC currents into components that we can use to check if everything is operating normally. We then look at one of the key protection equipments that we use, which are current transformers. We will look at how these equipments work before seeing how we connect them to the protection system. The other key measuring equipments that we use are voltage transformers. We look at the different types of VTs that we use and how we size them for use with protection systems. Before you can design a protection system, you need to know what happens during different types of electrical faults. We therefore look at what happens to the system voltages and currents for various fault situations. We then look at protection panels and wiring and see how the protection equipment is installed and put together. Circuit breakers are a key element in the electrical network as they switch the electricity on and off and are there to disconnect any faults quickly when something goes wrong with the system. We will look at the different types of circuit breakers and see how the control circuits interact with the protection and control systems. The main protection system that we will look at on this course is overcurrent protection. We'll look in detail at all of the different features of this important protection before finishing off by looking at its sister protection, earth fault protection. By the end of this course, you will hopefully have a greater understanding of what a secondary protection system does and be able to identify all of the key protection components that we use. I hope you enjoy the course and get something out of it. After the first module, in which we looked at the equipment that we use for the protection system, in this module, we look at the basic principles behind protection systems. By the end of this module, you will understand some of the principles behind protection systems, including the importance of clearing a fault quickly whilst keeping as much of the healthy system connected as possible. The aims of the course today are: show the basic principles of a protection system, look at what affects the fault clearance time, see how the protection system varies as the system voltage increases, a protection system is used to identify faults on an electrical system and then quickly isolate it, leaving as much of the healthy system connected as possible. The longer the fault stays on an electrical system, the more damage is done to the equipment and the greater the danger that the system voltage will collapse and damage any healthy equipment connected to it. The time taken to detect and then remove the fault is called the fault clearance time. The fault clearance time generally consists of the following elements: the protection relay detection and operating time. This can range from 10 to 1000 milliseconds and depends on the fault location and the severity of the fault. Next, we have the trip relay operation time. This is designed to be a quick relay and tends to operate from 5 to 10 milliseconds. And finally, we have the circuit breaker operating time. This can range from 20 to 30 milliseconds, as circuit breakers are designed to open very quickly. When a substation or network is first planned, system studies are done which will define how quickly any fault needs to be cleared. to prevent it causing harm to existing plant or a system collapse, where the generators supplying the power drop out of synchronism and disconnect. In one system that I installed in the Middle East, a new 400 kV network was planned that had a maximum clearance time of 100 milliseconds, which was particularly problematic as the only main protection relay that would operate this quickly was a prototype that was still in the testing phase. We had no choice but to select the relay, which added delays and risk to the project. The higher the system voltage, the higher the fault current and risk to the network, and the faster we need to detect and disconnect the fault. The main way that we can reduce the clearance time is by using more advanced protection equipment to more precisely identify the type and location of the fault and decide which circuit breakers need to be operated. Our aim with any protection system is not only to detect any fault quickly, but to keep as much of the healthy system connected as possible, to keep customers connected and therefore save money. This aim is called fault discrimination. To achieve good fault discrimination, we use a combination of parallel protection systems, all working together, to identify the position of the fault in the electrical network. As the system voltage increases, the protection system becomes more complex, and therefore more costly, so that it can deal with all of the potential faults that may occur, and still maintain good discrimination, so that customers are not incorrectly disconnected. Therefore, as the system voltage increases, the protection complexity increases, and the cost of the protection systems increase. For LV networks, the cost of a protection failing is not that significant in terms of replacement cost or the amount of customers disconnected, so we generally only have one protection system, such as overcurrent protection. On HV networks, primary equipment can be very expensive, and there are very serious implications for disconnecting thousands of customers, so the integrity of the protection system is taken more seriously. As the main system voltage increases, we also need to make the protection system more secure, and consider the possibility that a protection system may not operate when asked to do so. This is done by adding protection redundancy. We normally have 3 layers of protection: Main Protection System 1, Main Protection System 2, and a backup protection, which is normally overcurrent. These 3 protection systems usually work on different principles, operate in parallel, and are kept electrically independent, with each system being provided with its own current transformers, DC supplies, and wiring. Let's summarize what we've learned today. A clearance time after a fault includes the time for detection and the operating times, the trip relay, and circuit breaker. The aim of the protection system is to clearly identify the fault and remove it as quickly as possible whilst keeping the healthy system intact. As the system voltage of the network increases, the complexity and cost also increase, and the fault clearance times reduce. Congratulations for completing this module. You should now understand all of the features of a secondary protection system and how it operates to identify the fault and clear it quickly before damage is done to the system. This is an important topic, and understanding it is essential for the subject matter in the next module, so please go back and redo the modules that didn't make sense. I've attacked some questions on today's module to test your knowledge. Welcome everyone, my name's Stephen Brooks and I've created the Electrical Protection course. I've tried to write the course to make it accessible to everyone. including people without an electrical engineering background. Electrical protection is a key element in all electrical systems and ensures that the electrical network can operate safely and efficiently. This first protection course is the first in a series and will introduce all of the basic principles of electrical protection systems. The aim is that by the end of the course, you will have a good theoretical and practical understanding of electrical protection systems. This first section shows the symbols that we will use in protection schemes, introduces you to some of the equipment that we will come across, and shows how they all interact with each other to create a fully functioning protection system. I hope you enjoy this section and get something out of it. The aims of the course today are: describe the symbols and terminology that we will be using in this course, introduce all of the basic elements of a fully integrated protection system, show how the protection, control, and auxiliary systems connect together. You will come across the following symbols in this course. The first is the power source. This is where the power is generated. It could be a power station or a diesel generator. Next we have the load. This is where the energy of the system is used up. It could be a large motor, a kettle, or a washing machine. We always assume that the power flows from the power source to the load. Here's a typical three-phase system, with a three-phase power source containing red, yellow, blue, and neutral conductors, and a three-phase load containing red, yellow, and blue elements. To connect the power source to the load, we can either use cables, wires, or overhead lines. These are the typical symbols for the current transformer. These transform the thousands of amps on the primary system into a lower current level, so it can be used by the protection system. We then have voltage transformers. These are the two common symbols that we use. These transform the high voltages found on the primary system into a lower voltage that can be used on the protection system. To indicate the level of the currents and voltages on the system, we use ammeters and voltmeters. And we use them widely throughout the course to show what's happening with the currents and voltages. Circuit breakers are used widely throughout the system to switch the electricity on and off. These are the two common symbols for circuit breakers that you will find. We will use three conditions for the circuit breaker. The first one is when the breaker is switched off, when the breaker is closed, and when something goes wrong and the circuit breaker is tripped by the protection system. Here is the common symbol that we use for protection relays. The number or symbol inside the rectangle indicates the type of relay as per international standards. Primary equipment is defined as everything that is directly connected to the system voltage. This includes substation equipment, such as circuit breakers, isolators, and current transformers. Transformers. These change the system voltage from a high level to a low level. And finally, loads. Motors, kettles, washing machines. They use up the electrical energy of the system. Bus bars, cables, and overhead lines to take the electricity around the system. Secondary equipment is defined as the systems and equipments that control, monitor, and protects the primary system. A protection system consists of numerous separate elements all working together. These include circuit breaker control and protection, including circuit breaker control, where we open and close the circuit breaker via its operating mechanism, circuit breaker protection, where we protect the integrity of the circuit breaker, and synchronizing, where we ensure that the circuit breaker only closes when it's safe to do so. Next, we have the protection systems themselves. These include auxiliary relays that repeat signals and pass them on to other systems, trip relays that open the circuit breakers when a fault occurs, and finally protection relays. These continuously monitor the currents and voltages and make sure that the system is healthy. And finally, we have the control systems. We have equipment operation systems that allow you to remotely open and close all of the primary equipment. We have indication systems that show the position of all the circuit breakers, disconnectors, and other primary equipment. Alarm signaling. These tell the operators when something's gone wrong on the system. And finally, metering transducers. These provide indications of the currents, voltages, and other information on the system. Let's now see how the measurement, protection, control, and primary plant equipment fit together. First, we have the measurement equipment. This contains current transformers to provide information on the primary current, voltage transformers to provide the information on the primary voltage, protection equipment containing protection panels, relays, and systems, the control equipment containing mimic control panels and SCADA systems, and finally the primary plant such as circuit breakers. The current transformers feed current information into the protection systems and the control systems. And likewise the voltage transformers provide voltage information to these two systems as well. The control systems send signals to open and close the primary plant. And we then get status signals back from the primary plant to the protection and control equipment. Finally, when something goes wrong, the protection systems send trip signals to open the circuit breakers in an emergency. The actual interactions between the measurement, protection, control, and primary plant systems are obviously unique to each substation, but it is clear that all four elements work as one complete system. The complexity of these connections increase as the system voltage increases, with distribution systems having very simple protection and control systems, whilst high voltage substations have multiple layers of protection and several points of control. The one system we've not talked about is auxiliary systems. These sit in the background and keep the protection and control systems working. Firstly, we have the station services transformer, This transforms the voltage from the primary system into a lower voltage that we can feed into all the panels. We have the LVAC supply boards. These supply the low voltage to the protection and control systems. Finally, we have the direct current battery charger system. All substations need a backup electrical supply in case the main primary system fails. Let's see how the auxiliary systems fit together. First, we have the station services transformer connecting the primary network to the low voltage AC distribution system. This system then feeds auxiliary supplies including spring charging and panel lighting to the primary plant and protection and control systems. The low voltage system also feeds an AC-DC converter, which feeds the DC distribution board. This feeds the local control signals and the protection and control supplies to the protection and control systems. Finally, we have a battery. This is there to provide an emergency supply in case the primary network fails. Most high voltage substations have a battery that can provide a DC supply for up to 8 hours after the primary network has failed. This allows you to open and close the breakers and monitor the system until the supply from the main primary network returns. Let's summarize what we've learned today. Secondary equipment is defined as the systems and equipments that control, monitor, and protect the primary system. A substation protection system consists of measuring equipment, protection equipment, control equipment, and auxiliary systems. Auxiliary systems are provided to supply AC and DC supplies to the protection and control systems. Congratulations for completing the first section of the electrical protection course. Hopefully, you will now understand what a protection system looks like and why they are so important. I know we've covered a lot of ground today, so take some time to go back and do some of the course again. I've attached some questions on today's section to test your knowledge. In this section, we will look at three-phase currents. Before you can start designing a protection system, you need to understand in detail how the electrical network behaves when it is operating normally. Only then can you design a system that reacts quickly and decisively when things go wrong. By the end of this section, you will understand how the current vectors behave under normal conditions and how the current vectors can be analysed to obtain information to give us clues of a fault taking place. The aims of the course today are to introduce the principles behind three-phase current, to look at the current vectors in balanced and unbalanced systems, to introduce the principles of positive sequence, negative sequence, and zero sequence currents. A three-phase distribution system contains all three phases and a neutral. This is called a three-phase and neutral, or TPN system. Let's look at the current. Firstly, we have a three-phase source with red phase, yellow phase, and blue phase output, and a neutral. We have a three-phase load with red, yellow, and blue elements. We have three-phase conductors, red, yellow, and blue, and finally a neutral conductor. The red, yellow, and blue phase currents will go through the load and head back to the neutral point of the source. Let's see what happens when they come together. The neutral is where the red, yellow, and blue phase currents come together. To study what happens, let's consider two conditions: balanced loads and unbalanced loads. In a balanced load, all three phase currents are equal, separated as usual by 120 degrees. The magnitude of the vectors depends on the loads on the system. The currents all come together on the neutral. Therefore, the red phase, yellow phase, and blue phase current vectors all merge together. We can see that all three phase current vectors cancel out. Therefore, in a balanced three-phase system, the neutral current equals zero. Let's now look at unbalanced loads. In an unbalanced three-phase load, the three-phase currents are not equal in magnitude, but they are still separated by 120 degrees. In this case, the blue phase current is less than the others. Again, the red phase, yellow phase, and blue phase current vectors merge together on the neutral conductor. We can see that the three current phases do not cancel out, and there is now a neutral current. This flows back to the neutral point of the source. Therefore, in a TPN system, the current on the neutral varies between 0 for a balanced three-phase system, right up to the full phase current when only one phase is loaded. We therefore have to make the neutral conductor the same physical size as the phase conductors, as it may carry the same current as them. We have to consider the neutral conductor as live, as it carries current. If we now summate the red, yellow, blue and neutral currents, they will always balance out and equal zero. In transmission systems, we don't normally have a neutral. Let's look at the currents. Here's the three-phase system without the neutral conductor. The currents now act in a balanced circular motion, and the direction of the currents in each phase continuously changes, depending on the magnitude of the loads imposed on each of the three phases. For the transmission system, all we are doing is taking power from the source to the destination, and we don't need phase to neutral voltages. There is therefore no point paying for the neutral conductor, and we have a TP system. Customers require a phase to neutral voltage on the distribution, and a neutral is therefore required, so we have a TPN system. In a transmission system with no neutral, the current phasor diagram looks like this. This is called a three-phase or TP system. Let's now add the three phases together. The three current magnitudes may vary in magnitude and change direction, but the vector sum of the three-phase currents will always equal zero. We can also break down the three-phase vectors in terms of positive sequence, negative sequence, and zero sequence components. These three components vary in magnitude and angle, depending on how the system is behaving. Let's now change the system parameters and see how the components vary. To understand this a bit better, let's work backwards and look at the three types of sequence vectors. The first is positive sequence. These vectors spin in an anti-clockwise direction: red, yellow, blue. Next we have negative sequence. These vectors spin in a clockwise direction: red, blue, yellow. And finally, we have zero sequence vectors. These vectors have a magnitude, but no spin. Let's now vary the system parameters and see how the three components vary. Firstly, we have a balanced load with no faults. In a balanced healthy system, where all three currents have the same magnitude and there are no faults, the positive sequence vectors that are created by the generator appear at the load. There is no negative sequence current. There is also no zero sequence current. The next condition is an unbalanced load with no faults. In an unbalanced healthy system, where the three-phase currents have different magnitudes and there are no ground faults, the generator still supplies only positive sequence vectors. The supply at the load now also contains negative sequence vectors, which makes the supply unbalanced. There is still no zero sequence current. Finally, let's look at an unbalanced load with a ground fault. When a ground fault occurs, all three-phase vectors move by a certain magnitude away from the center. In an unbalanced, unhealthy system, where the three currents have different magnitudes and there are ground faults, the generator still supplies only positive sequence vectors. The supply at the load now also contains negative sequence vectors. The supply at the load also contains zero sequence vectors. Why do we bother doing this? Well, we can use the information from the three components to analyze how the system is functioning. Digital relays use numerical analysis to obtain the three separate components in real time. The zero sequence currents are particularly useful, as you only get zero sequence currents when a ground fault occurs. This information can be used by main protection as a double check to make sure that a fault has actually occurred. Another feature of an alternating current system is the ability to use harmonic analysis to break down the sine wave into smaller sine wave components that have a higher frequency. We tend to group them into multiples of the original frequency. So if we have a standard 50 Hz sine wave, a sine wave with 3 times the original frequency, 150 Hz, would be classed as a third harmonic. 5 times higher, 250 Hz, would be classed as a fifth harmonic. And 7 times higher, 350 Hz, would be classed as a seventh harmonic. Some equipment on the system can cause harmful harmonics. They can reduce the lifespan of primary plant, such as transformers. Typical equipments that cause harmful harmonics include fluorescent lighting, capacitor banks, inverters, and some motor drives. We can use real-time analysis to identify certain harmonics in the system to support or block protection systems. Examples of these include the second harmonic. Higher levels of the second harmonic can occur when a transformer is energized, causing large amounts of current to flow into it, causing an effect called magnetic inrush. This can cause maloperation of the main protection relays. Some transformer protection relays use second harmonic blocking to inhibit the main protection until the transformer is fully magnetized and the magnetic inrush subsides. The third harmonic. Higher levels of the third harmonic can create hazardous oscillations in the three-phase network and create higher than normal currents flowing back through neutral wires. The fifth harmonic. High levels of the fifth harmonic can cause overheating in motors, as they can push against the motor's natural rotation. Harmonics are an unavoidable feature of an alternating current system that can be useful indications of equipment going faulty, but can also have serious consequences for an electrical utility. I once worked for a client in London who had to replace over 2,000 televisions for customers, all located in the same area. Upon further analysis, it was found that an old power factor compensation unit was causing serious harmonic distortions that caused the damage. Let's summarise what we've learned today. In a three-phase TPN system, the neutral current varies from zero in a balanced load right up to the full phase current when only one phase is loaded. If we summate the three-phase currents in a TP three-phase system, we get zero. We can split any three-phase current into numerous harmonics, which have a higher frequency than the principal current. We can split any three-phase current into three subcomponents: positive sequence current, negative sequence current, and zero sequence current. Congratulations for completing this module. You should now be familiar with three-phase currents and how their components can be analysed to work out if the system is behaving normally or not. This is an important topic, and understanding it is essential for the subject matter in the next module. So please go back and redo the sections that didn't make sense. I've attached some questions on today's module to test your knowledge. In this next section, we will look at one of the key primary equipments that we use, which are current transformers. We will show all of their key features and how they operate during normal and fault situations. This will allow you to understand all of the parameters that you will find on a CT rating plate. The aims of the course today are to introduce the basic principles behind current transformers, to show the fundamental terms that define a current transformer, to look at what happens when a current transformer is energized, loaded, and then saturated. If we place a high turns winding around a conductor carrying current, the electric field of that conductor will induce a small representative current in the winding. This device is called a current transformer, or CT, and is used for measuring purposes. The value of the current, ICT, will depend on the number of turns on the current transformer, where ICT equals the current flowing through the conductor divided by the number of turns on the CT. Let's do a worked example. Calculate the value of the secondary current, ICT. From the previous equation, ICT equals the current flowing through the conductor divided by the turns ratio. In this case, this equals 1600 amps divided by 900, which is the turns ratio, equals 1.77 amps. The CT current is a direct representation of the main conductor current. CTs are used widely in electrical systems to monitor the main currents, ensuring that the system is healthy. The ratio of the CT depends on the application. Let's look at the key elements. Here we have a 1200 to 1 CT. The larger figure is called the primary ratio and is normally equal to the full current rating of the circuit being protected. So if we had a 2000 amp rated bus bar, all of the CTs would have a primary ratio of 2000 amps. The smaller figure is called the secondary ratio. This is normally chosen as 1 amp or 5 amp, dependent on the requirements of the secondary protection relays. The current transformer is a magnetic device which generates a current and a voltage. Let's look at the relationship between the two as the current increases. Let's first draw the graph with voltage on the left-hand side and current across the bottom. If we now inject current into the secondary side of the CT and measure the voltage, this is the characteristic we'll achieve. This is one part of something called a hysteresis curve, which is what happens when you magnetize something that has a metal core. The initial part of the curve is called the magnetization phase. Next we have the linear phase. Following this is the pre-saturation phase. And finally, the saturation phase. Let's look at these 4 different phases in more detail. Let's look first at the magnetization phase of the curve. During the magnetization part of the curve, the secondary current is not a linear representation of the primary current due to the excitation current needed to magnetize the device, which is obviously an issue. Current transformer designers therefore try and minimize this part of the curve as much as possible by using special, high permeability magnetic materials. During the linear part of the curve, secondary current gives an accurate representation of the primary current, with some slight errors due to the excitation current. As a protection designer, we would obviously like the current transformer to stay linear for the maximum conceivable primary current. Next we have the pre-saturation phase. Like all magnetic devices, when the current reaches a certain level, the core starts becoming saturated. During this phase, the CT starts becoming non-linear. It's really important for protection designers to know when the current is becoming non-linear, so we've created a parameter called the knee point voltage. The knee point voltage, Vk, is the precise point on the curve when a 10% increase in the CT voltage will produce a 50% increase in the current. These parameters are shown on a curve. We assume that below the knee point voltage the current transformer is operating in a linear manner, and above the knee point voltage the current transformer is becoming saturated and is no longer operating linearly. Our aim is obviously to stay within the linear zone of the CT, as outside this zone, the secondary currents may no longer represent the primary values, and the CT may stop generating secondary current altogether. The minimum knee point voltage required is defined by the protection designer, who will undertake a fault study that defines the likely currents involved. The CT designer will then take this information and decide how to create a CT that can meet the knee point voltage, while still maintaining the other parameters required. The final stage is when the CT becomes saturated, becomes nonlinear, and stops functioning as a current transformer. When a core becomes saturated, it stops generating secondary current. During this stage, the protection system will only see the DC resistance of the current transformer. This is the reason that the DC resistance is a key element of the current transformer design. Here we have a typical feeder circuit. Let's now connect the current transformer to an ammeter so we can measure the current. Let's now close the circuit breaker. The primary current will now increase through the current transformer. As soon as current starts flowing, we quickly go through the magnetization phase. Let's now increase the primary current. As we can see, as the current increases, so does the voltage. Because the primary current is well below the 1600 amp capacity of the CT, the current transformer operates at the bottom end of the linear phase. Let's now apply a high resistance fault to the feeder. The primary current now increases substantially, but as it's a high resistance fault, the current is limited, and we therefore still operate in the linear zone. Let's now apply a full unrestricted fault to the feeder. The primary current now goes beyond the capacity of the CT, and the characteristic goes into the saturation zone. The actual way the CT will respond to these different currents depends on the design of the CT. This is a typical operating characteristic for a feeder protection current transformer, which is designed to operate during both normal and fault conditions. When the primary current is less than the rated current of 1600 amps, the CT will normally operate at the bottom of the linear range. When we get a fault condition, we ideally want the current transformer to remain in the linear range for as long as possible, as we need the information from the currents to identify and locate the fault. Unfortunately, for some serious fault conditions, this goal is unachievable, as the high currents involved would saturate any CT that we could provide. By varying the core materials, physical shape, number of turns, and secondary wiring wire diameters, we can vary all of the CT parameters, including the following: the CT ratio, the CT burden, how much load the CT can carry, the excitation current, the DC resistance, and finally, the knee point voltage. Let's summarize what we've learned today. Current transformers allow the high currents found on the primary network to be monitored by the secondary systems. As the current on the CT increases, it passes through several phases before becoming saturated. The knee point voltage of a current transformer is the boundary at which it starts becoming nonlinear. Congratulations for completing this module. You should now be familiar with current transformers and understand why they are such an important component in the protection system. I've attached some questions on today's module to test your knowledge. In this module, we will leave the theory behind and start looking at the practical side of protection systems by looking at how we use current transformers, connect them together, and feed the protection and control circuits. The aims of the course today are to look at the different types of CTs that we use on the primary network, to show how a current transformer should be connected in an electrical circuit, to look at the different classes of CTs that we use and their differing characteristics, the most common symbols for a current transformer are shown below. For a single-phase CT, we have this symbol or this symbol. For a three-phase CT, we use this symbol or this one. CTs are used throughout the electrical system. Here are the most common types. Firstly, we have the bar type, where the CT is constructed as part of the bus bar. These are used in distribution systems up to 11 kV. Next, we have the ring type. These slip over the bus bar or cable being measured. These are used in indoor distribution and transmission systems. Finally, we have the post type. These are used in outdoor distribution and transmission systems. It is very important which way the CT is physically connected, as it defines the direction of the secondary current flow. Here we have a CT monitoring a bus bar. Common nomenclature is the following. On the primary high current side, we label the terminals P1 and P2. On the secondary low current side, we label the terminals S1 and S2. Let's now add some current on the primary side. The first thing to note is that the current on the secondary side flows in the opposite direction to the primary side. The current flows from S1 through the relay and back to S2. If we reverse the flow of primary current, the secondary current now flows in the opposite direction. This is why it's so important to get the orientation of P1 and P2 correct. The P1-P2 orientation is physically printed on the outside of the CT and appears in every single layout and protection diagram. The direction of the primary current is critical in metering as it defines the power flow, and in protection circuits where we may be sharing current information across multiple circuits and systems or connecting CTs in parallel. Different utilities have different rules on which way in the circuit P1 and S1 are physically positioned. A common standard in use has the P1 and S1 nomenclatures facing the circuit breaker. Where there are no circuit breakers, P1 and S1 nomenclatures face the equipment that's been protected. So if we position the CT next to a circuit breaker, P1 and S1 physically face the circuit breaker. We normally have multiple electrically independent current transformer windings housed in the same unit. When this happens, we have to give them all the same orientation. Here we have a CT with 4 windings. As usual, we orientate them with P1 facing the breaker. We call the individual current transformers cores and number them sequentially from the P1 orientation. Let's do a worked example. Here we have a transformer. How would we label the CTs? P1 and S1 face the item which is being protected, which in this case is the transformer. Therefore, we orientate the CTs as follows. Inside substations, current transformer types tend to fall into one of the following groups. Metering CTs, used to accurately measure the value of the current on a bus bar or electrical cable so that the customer can be billed. They're designed to be very accurate, from a very low current level up to 120% of the full circuit current rating. They have a low excitation current, which leads to minimal errors at very low currents. Next, we have protection CTs. These are used to accurately measure the value of the current on a busbar or electrical cable. Are designed to be reasonably accurate, from a low current level up to a multiple of the circuit rating. Have a reasonably high knee point voltage, so that the current can be measured accurately during a fault situation. When defining protection CTs, it is useful to know how accurate the CT will be over its linear range. You will often see this labeling system used. 5P10, where the first number represents the accuracy, so in this case it will be 5% accuracy. The 10 represents the range over which the CT is accurate, so for this case the CT is accurate up to 10 times its primary current rating. Let's do a worked example. For the following protection CT, what is its nominal accuracy, and at what current does it stop being accurate? It's a 5P20 CT, so therefore its nominal accuracy equals 5%. For a 5P20 CT, its accuracy range is up to 20 times the primary rated current. Therefore, accuracy range equals 20 times by the primary rated current, which is 1600 amps, equals 32,000 amps. So during a fault condition, as long as the current does not exceed 32,000 amps, the secondary current will be an accurate representation of the primary current. Finally, we have special protection CTs, sometimes called Class X. HV protection needs precise information on the current, even during a fault situation, so that the position of the fault can be precisely located. Class X CTs are designed to perform this purpose and have a minimum knee point voltage. This is defined by the protection equipment's characteristics, so that the information about the current vector is fed to the protection equipment for as long as possible after the fault occurs. We normally ground one side of the current transformer, as we can get high capacitive voltages generated into the secondary circuits when certain conditions arise. This is normally done through a disconnecting link, which can be removed when the current transformer is being tested. The choice of whether we ground S1 or S2 depends on the protection system design. We often connect the CTs in parallel and feed the output into one protection system to compare the currents that are flowing in multiple circuits at the same time. Here we have feeders 1, 2, and 3, with the P1 floor current transformers facing the breaker. We connect all the CT S1 connections together and feed them into the protection panel. We do the same with all the S2 connections. We've now paralleled the CTs on all three circuits. When we do this, we need to ensure that all of the CTs will have the same design and that the P1, P2 orientations match. For grounding the CTs, we use one single link located in the protection panel. When we parallel CTs, it is very important that their characteristics, i.e. ratio, knee point voltage, accuracy, and resistance, are closely matched. Otherwise, we will get output differences between them that may lead to the protection systems maloperating. This can be a big issue when we are adding a new feeder onto an existing substation, where we need to match with CTs that may have been designed 30 years ago. Current transformers should never be open-circuited whilst current is flowing through the primary, as dangerously high voltages will be generated in the secondary winding. To prevent this happening, special shorting terminals are provided on all current transformer circuits. Here we have a three-phase CT, red, yellow and blue. We feed all of the CT wiring into the terminal block. This allows us to modify the circuits at a later date. We connect all the neutrals together and take them down to ground through a link. We then feed the red, yellow, blue and neutral wires to the secondary circuits. The terminals have an inbuilt shorting link across the red, yellow, blue and neutral wires. If we need to do any work on the secondary circuits, this link can be pushed across, shorting the CTs. Here's some examples of the types of terminals available. Let's summarise what we've learned today. Current transformers are defined by their ratio, need point voltage, DC resistance and burden. We use different classes of current transformers for different protection purposes, including metering and protection. Current transformers should never be open-circuited, and special terminals are used to ensure this doesn't happen. Congratulations for completing this module. You should now understand all of the features of current transformers and how we can connect them to the external systems that they feed. I have attached some questions on today's module to test your knowledge. In this module, we will look at the other main primary measuring device that we use, which are voltage transformers. In the same way as we looked at current transformers, we will learn how voltage transformers operate and how they should be connected to the secondary protection system. The aims of the course today are: introduce voltage transformers and show the different types that are used on the electrical network. Show the primary and secondary connections for voltage transformers. Show how the burden on a voltage transformer can be calculated. You will come across these typical symbols for the voltage transformer. Either this symbol or this one. A magnetic voltage transformer is simply a high ratio transformer that reduces the system voltage down to a low voltage level that can be used in the secondary protection system. Here's a typical voltage transformer connection. We call the high voltage winding the primary and the low voltage winding the secondary. On the primary, we have the turns ratio NP. We have a primary voltage and a primary current. On the secondary, we have the primary turns ratio and S. We have the secondary voltage Vs and the secondary current Is. By knowing the precise number of turns in each winding, we can work out the voltage transformer turns ratio, which establishes the ratio of the currents and voltages. The voltage transformer turns ratio equals the number of turns on the primary divided by the number of turns on the secondary, equals NP divided by NS. The voltage ratio equals the voltage on the primary divided by the voltage on the secondary equals Vp divided by Vs. Most substation voltage transformers have a secondary line voltage of 110 volts. To achieve this secondary output voltage, we require the following turns ratio on the voltage transformer. For a system voltage of 11,000 volts, we require a turns ratio of 100. For 400,000 volts, we need a turns ratio of 3,636. Because of the construction costs involved, we find that magnetic type voltage transformers are only used on system voltages up to 33 kV. Above this level, other types of voltage transformers are used. A popular alternative at high voltage levels are capacitor voltage transformers. We use a capacitor voltage divider to reduce the voltage to an acceptable level. We connect one side to the HV network and one side to the ground. We then step down the voltage using the transformer, and the output is the VT secondary terminals. A recent addition are optical voltage transformers. These use something called the Faraday polarizing effect and utilize a fiber optic cable wrapped around the HV terminals. As the primary voltage changes, this affects the phase shift of the optical signal, which can then be processed. Voltage transformers, or VTs, are designed to deal with any impulse voltages, i.e. overvoltages, that may occur on the primary network. On distribution systems, up to 36 kV, the VTs tend to be three-phase devices. Above this voltage level, they tend to be single-phase devices. We normally have multiple secondary windings on the voltage transformer to feed all of the different protection circuits. MCBs are provided for the live and neutral output of all LV windings. A HV fuse is also provided as a last resort to protect the primary winding from a short circuit on the VT or the secondary winding. It is quite common for one VT to be provided on the bus bar, which then supplies a voltage input to all of the individual incomer and feeder protection systems. When this is done, separate MCBs are provided for each panel to allow for isolation of each circuit for maintenance. It is important that we never parallel the secondary outputs of two separate VTs, as dangerous circulating currents can occur between the secondary windings. Where we have multiple bus bars and VTs, we switch the VT outputs so that when the bus section breaker closes, one VT is disconnected and all panels are fed from a single VT source. Here's an example of that. As the bus section breaker closes, we switch the supplies from one VT to the next. Busbar VTs are used widely in distribution networks, as the protection systems tend to be quite simple, and we don't need a separate feeder voltage unless we are synchronizing between different networks. The circuits to switch to voltage supplies can become extremely complex, and can use up valuable circuit breaker auxiliary switches. The accuracy of voltage transformers is not normally a consideration, unless the voltage output is required for metering purposes. Specialist high accuracy metering, or HAM, voltage transformers are used on industrial circuits, which can have an error factor as low as 0.2% across the full transformer rating. On high voltage systems, we combine the voltage transformers and current transformers into one HAM unit. A key element of voltage transformer design is the burden, which is basically the maximum power output of the secondary windings measured in VA. To calculate the burden required, we simply add up the loads of all the equipment connected to it, and then add a suitable percentage for future capacity. When dealing with busbar VTs, we assume the worst case, and assume that one busbar VT feeds all of the feeder panels. Let's do a worked example. A busbar VT feeds 4 feeder protection panels. Calculate the VT burden required. The first stage is to look at each panel individually and calculate its burden by looking at the burdens of the equipment inside it. This information can be found on the equipment rating plate or manufacturer's catalogue. Let's now break the panel down into its individual elements. Firstly, we have a feeder protection relay. Looking at the catalogue, this has a burden of 5 VA. Next, we have an auxiliary relay. This is a burden of 2 VA. There's 4 relays, therefore the total burden is 8 VA. Next, we have another feeder protection relay with a burden of 5 VA. And finally, we have some transducers. These have a burden of 3 VA. We have 2 transducers, therefore the total burden is 6 VA. We can then calculate the total burden for that panel type. From the previous slide, burden per panel equals 5 VA plus 5 VA plus 8 VA plus 6 VA equals a total of 24 VA per panel. The burden for 4 panels is 24 VA multiplied by 4 equals 96 VA. It is good practice to add a hefty percentage for future substation expansion and transient loads, as replacing a voltage transformer is a difficult thing to do. Therefore, let's double the burden shown to give a total VT burden of 192 VA. In older systems, the voltage transformers were a lot larger, as the older electromechanical relays had a large burden, which drew a large amount of power from the VT. Modern microprocessor relays draw a very low burden from the system, and the VT sizes can be significantly reduced. Let's summarise what we've learned today. Voltage transformers are used throughout the electrical network for measurement and metering purposes. Voltage transformers should never be connected in parallel. The burden of the VT can be calculated by adding together all of the potential loads on the VT. Congratulations for completing this module. You should now understand how we use primary measuring equipment to feed the secondary protection systems. In the next module, we will learn how the information provided by the current and voltage transformers is used to detect faults. I've attached some questions on today's module to test your knowledge. In this section, we will start looking at the theory of secondary protection systems by introducing some of the basic principles behind fault detection. Our aim is to detect faults quickly and accurately, so that we minimize the impact on the equipment and network and keep as many customers connected as possible. This section shows what happens to the voltages and currents for each of the different types of fault. The aims of the course today are: introduce the different fault types that can happen on an electrical network. Analyze what happens to the voltages and currents under each fault scenario. Let's see how the currents and voltages behave in a normal three-phase system. Here's a typical three-phase system with a three-phase source and a three-phase load. Let's now energize the system. During a normal condition, the three-phase voltages will normally be balanced. To calculate the line voltages, we add the two-phase voltages together. Let's do that for each of the line voltages. The magnitude of the three-phase currents depends on the impedance of the loads and cables connected to the source, so these continuously vary. The angle between the current and voltage vectors also depends on the connected impedance, and again is continuously changing. The impedance of the line consists of resistance, inductance, and capacitance, which applies down the full length of the overhead line or cable. These will produce a total impedance for the line, which is called the characteristic impedance. The impedance of the load is normally inductive, but will obviously depend on the types of loads connected. For the transmission system, this load value will consist of thousands of individual impedances combined together. If we now try and summate all of the currents, it will equal zero, as the current flowing out through the phases balances out with the currents flowing back through the neutral. Let's now see what happens if we have a phase-to-earth fault. Once the conductor touches the ground, earth fault current will start to flow from the blue phase conductor through the ground and back to the generator neutral point. If we look at the impedance of the fault, all it contains now is the impedance of the conductor up to the point of the fault, the impedance of the fault itself, and the impedance of the ground. This combined impedance is far lower than the impedance of the load. Let's now see what happens to the voltages and currents. The voltages and currents on the red and yellow phases may be slightly affected by the blue phase going faulty, but are likely to stay pretty much the same. On the faulty blue phase, the impedance has dropped substantially, as the load impedance is no longer connected. The current therefore increases substantially. The blue phase voltage will fall to match the 0 volts of the ground. Let's now look at the line voltages. The red to yellow line voltage has not been affected and stays the same. The red to blue and yellow to blue line voltages are both changed in their magnitude and angle as the blue voltage has reduced. If we now summate all of the currents, it will now no longer equal 0, as some current is leaking out of the system into the ground. Let's summarize what happens for a phase-to-earth fault. Current increases considerably on the faulted phase, as the impedance of the load is bypassed. The voltage drops considerably on the faulted phase, as it is dragged down to match the voltage of the ground. The summation of the three-phase currents no longer equals zero, as current is now leaking out into the ground. The direction of the current changes on the faulted phase, as it no longer flows from the source to the load. Let's now look at a red phase to neutral fault. Once the red phase touches the neutral, current will start to flow from the red phase conductor through the neutral and back to the generator neutral point. If we look at the impedance of the faulted circuit, all it contains now is the impedance of the conductor up to the point of the fault, the impedance of the fault itself, and the impedance of the neutral conductor. This combined impedance is far lower than the impedance of the load. Let's now see what happens to the voltages and currents. The voltages and currents on the yellow and blue phases may be slightly affected by the red phase going faulty, but are likely to stay pretty much the same. On the faulted red phase, the impedance has dropped substantially, as the load impedance is no longer connected. The current therefore increases substantially. The red phase voltage will fall to match the 0 volts of the neutral. Let's now look at the line voltages. The blue to yellow line voltage has not been affected and stays the same. The red to yellow and red to blue line voltages are both changed in their magnitude and angle, as the red voltage has reduced. If we now try and summate all the currents, it will still equal 0, as although the currents have increased, there is no current leaking out of the system. Let's summarize what happens for a phase to neutral fault. Current increases considerably on the faulted phase, as the impedance of the load is bypassed. Voltage drops considerably on the faulted phase, as it is dragged down to match the voltage of the neutral. The summation of the three-phase currents still equals 0. The direction of the current changes on the faulted phase, as it no longer flows from the source to the load. Let's now see what happens if the yellow phase conductor touches the blue phase conductor. Current will now start to flow from the yellow phase conductor through the fault and back through the blue phase conductor. If we look at the impedance of the faulted circuit, all it contains now is the impedance of the yellow phase conductor up to the point of the fault, the impedance of the fault itself, and the impedance of the blue phase conductor. Let's now see what happens to the voltages and currents. The voltages and currents on the healthy red phase are likely to be substantially affected, as we are disconnecting the power on 2 of the 3 phases. Here we have shown the red phase voltage increasing slightly, and the current staying the same, but the actual effects will depend on the load impedances and load types. On the faulted yellow and blue phases, the impedance has dropped substantially, as the load impedance is no longer connected. The current therefore increases substantially on both phases. It flows from one phase into the next, and is one of the few times we actually see line current. The current vectors reflect this, with the yellow current being 180 degrees out of phase to the blue current. The yellow and blue phase voltages have reduced in magnitude. The angle between them has reduced and is driven by the impedances of the line conductors. Let's now look at the line voltages. All three line voltages will change as the red phase voltages increased and the yellow and blue phase voltages reduced. If we now try and summate all the currents, it will still equal zero, as although the currents have increased, there is no current leaking out of the system. Let's summarize what happens for the phase-to-phase fault. Current increases considerably on both faulted phases, as the impedance of the load is bypassed. Voltage drops considerably on both faulted phases. The angle between the voltages and their magnitude depending on the line impedance. The summation of the three-phase currents still equals zero. The direction of the current changes on the faulted phases, as they no longer flow from the source to the load. Finally, let's now look at a full short circuit across all three phases. The impedance of the faulted circuit now represents a balanced fault, consisting of only the phase conductor impedance on each leg. Let's see what happens to the voltages and currents. As we can see, all three-phase current magnitudes increase significantly and flow equally between the three phases. We now have line currents instead of phase currents. All three-phase voltages will now reduce substantially, but they will remain in phase as the voltage is balanced. Let's now look at the line voltages. All three line voltages will now reduce, as the phase and neutral voltages have reduced in magnitude, although they will remain at the same angle. If we now try and summate all the currents, it will still equal zero, as although the currents have increased substantially, there is no current leaking out of the system. Let's summarize what happens for a full short circuit. Current increases considerably on all of the phases, as the impedance of the load is bypassed. Voltage drops considerably on all the phases. The angle between the voltages and their magnitude stay equal, as it's a balanced fault. The summation of the three-phase currents still equals zero. Let's summarize what we've learned today. The effects on the system of a fault depends on the position of the fault and the line impedances. Different types of fault have different effects on the phase voltages and currents. You should now understand how the different fault types affect the currents and voltages on the network. This is a key section, so please do not hesitate to go back and do parts again if something doesn't make sense. I have attached some questions on today's section to test your knowledge. In this module, we will look in detail at protection panels. These house all of the protection and control equipments that we use, and it is interesting to study how they are constructed. I'll look at some of the equipments that they contain, some of which only appears in protection systems. The aims of the course today are: introduce the panel types for the three main protection systems. Look at some of the key equipment that you will find on panels and how they work. Introduce the wiring and terminal types that make up the secondary systems. Panels come in all shapes and sizes and are used throughout the electrical network to house the secondary equipment. The main types of panel we use are protection panels. These house all the main protection relays and systems that detect faults and keep the network operating safely. Control panels. These allow the operator to open and close all the primary plant and provide indications on how the system is performing. Auxiliary panels. These contain all the backup low voltage and DC systems that support the protection and control panels. Let's look at a typical protection panel. Firstly, we have a metal panel frame containing a 19-inch or 482mm wide rack system. This rack system allows the size of the main protection relays and equipments to be standardized at a width of 19 inches. The height of the equipment are also standardized, using what's called a U system, where 1 U equals 44.5mm. So therefore, for the single tier rack that's 1 U high, we'll have a width of 482mm and a height of 44.5mm. Let's now look at a typical MMIC control panel. We have a single line diagram representing the electrical configuration of the network, showing all the transformers, bus bars, and primary plant. We have semaphores for the primary plant, whose position is being monitored or controlled, normally the circuit breakers, isolators, and earth switches. Semaphores fall into two categories. Firstly, we have indication only. These light up or rotate as the primary equipment is opened or closed, indicating the change in status. Let's see how that works in practice. So here we have a semaphore indicating that the breaker is closed. If the circuit breaker is now opened, the semaphore now goes horizontal to indicate the new breaker position. If the status isn't clear, or the power supply is lost, the semaphores go into a defined state, which shows the indication can't be trusted. The second type is controlling indication semaphores. These are dressed or rotated by 45 degrees, which then send a signal to the primary equipment to open or close. During this state, the semaphore flashes intermittently. So here we have a semaphore indicating that the breaker is closed. Let's now rotate it so that we can open the circuit breaker. The semaphore flashes until the breaker has changed position. Once the circuit breaker is opened, the semaphore moves to indicate the new position. Let's now reverse the process and rotate the semaphore to close the circuit breaker. Again, the semaphore flashes until the breaker has changed position. Another device you will see inside control panels are transducers. The first type is a voltage transducer. Here's the symbol we normally use. These are fed from the voltage transformer AC output, normally a phase voltage of 63.5 volts, and produce a DC output of 0 to 10 milliamps, where 10 milliamps represents a full voltage of 63.5 volts. Next, we have a current transducer. This is the symbol we normally use. These transform the current transformer AC output, normally 1 amp or 5 amp, and produce a DC output of 0 to 10 mA, where 10 mA represents full output current. Next we have a frequency transducer. This is the symbol we normally use. These transform the voltage transformer AC phase output, normally 63.5 volts, and produce a DC output of 0 to 10 mA, where 10 mA represents the full system frequency, either 50 Hz or 60 Hz. Finally, we have Watts transducer and Vars transducer. These transform the voltage transformer and current transformer outputs and produce a DC output of minus 10 mA to plus 10 mA, where minus 10 mA represents full power flowing in the reverse direction and plus 10 mA represents full power flowing in a forward direction. Most utilities have a wire ferruling or labeling system whose prefix identifies each unique circuit type. A typical system is shown below. These ferrules are also shown on the schematic design drawings and wiring diagrams, which allow the substation to be constructed as per the design. The unique ferrules make testing and commissioning easier, allow the engineers to find any faults quickly, and allows the system to be expanded easily in future. Terminals and links are used in protection and control systems for the following reasons: to join the wiring for two protection systems together, to provide isolation points in the system for maintenance, to provide access points in the system for testing and measurement. There are obviously many different terminal types and manufacturers. Let's look at the most common. Firstly, we have the standard terminal. The standard terminal is used to connect two wires together and interconnect protection systems. They're suitable for standard wiring up to 4 square millimeter. The terminals are spring-loaded, forcing the user to push down on the screw to release the crimp. This improves security. Next, we have SCADA terminals. These are low-current terminals used to take signals to the supervisory, control, and data acquisition system. In the middle of the terminal, we have a knife isolation link to allow the incoming and outgoing signals to be segregated. This is used for testing purposes. Finally, we have current transformer terminals. Current transformers cannot be left open-circuited. CT terminals are designed to avoid this happening. All the connections are via a bolted connection to provide more security and carry the high currents associated with current transformers. In the middle of the terminal we have a shorting link, which can be used to short the CT before the outgoing wiring is accessed. If an energized CT is left open-circuited for even a few minutes, the internal voltages generated can damage the main windings, which will mean the replacement of the current transformer, an expensive business. This limitation needs to be designed into the CT schematics and wiring during the design phase and built into any maintenance schedules to ensure that it cannot happen under any circumstances. Every utility has its own standard for wiring, but most protection systems use 2.5 square millimeter stranded conductor, with larger conductors used as required. A typical color code for protection wiring is shown below. For the AC supplies, we have brown for live and black for neutral. For DC wiring, we tend to use grey wiring. For the red phase CT, we use red wiring, yellow phase we use yellow wiring, and blue phase we use blue wiring. For any earth wires, we tend to use green wiring. Crimps are widely used in protection and control wiring, as they give a more secure connection into the terminals than just using bare wire. Here are some typical types and their application. The first type is the hooked blade. These are used for most connections. The hook on the end of the crimp forces the user to push the screwdriver into the terminal to release it, making accidental disconnection more unlikely. Next is the ring type. These are used for the bolted connections associated with current transformers. They can carry a high current and are very secure. Finally, we have the pin type. These are used for low current, SCADA and monitoring circuits. Let's summarize what we've learned today. Different panel types are provided for the protection, control, and auxiliary systems. The types of terminals used on the secondary wiring need to match the function of the systems connected. Panel wiring needs to be color-coded and ferruled to make installation, testing, and maintenance easier. Well done for completing this module. You should now understand how protection panels are constructed and be able to identify some of the key equipment that they contain. I've attached some questions on this module to test your knowledge. In this section, we will look at circuit breaker controls. Circuit breakers are the main device that we use to switch the electricity around the network and for disconnecting faults as they occur. In this section, we will look at the different types of circuit breaker and how the secondary protection system interacts with the breaker's control circuits. The aims of the course today are: look at the key features of circuit breaker mechanisms. See how the closed circuit is constructed with all of the different control elements. Look at the trip circuit and compare how it differs to the closed circuit. As the amount of current and voltage that needs to be carried increases, the circuit breaker type changes. Let's look at some typical circuit breaker types. First, we have the miniature air circuit breaker, or MCB. These are rated up to 32 amps. Next, going up the current scale, we have the molded case air circuit breaker, or MCCB. These are rated up to 64 amps. Next, we have the air circuit breaker, or ACB. These are rated up to 630 amps, and is the biggest LV breaker that we use. Increasing the system voltage and the current now, we have the vacuum circuit breaker, or VCB. These are used on system voltages from 6.6 kV to 36 kV, and up to a current rating of 2000 amps. This is the main breaker that we use on the distribution system. Increasing the system voltage now, we have the three-phase gas-insulated, or SF6 circuit breaker. These are used on system voltages from 66 kV to 132 kV, and up to a current rating of 3000 amps. Finally, we have the highest rated circuit breaker we can buy, which is the single-phase gas-insulated circuit breaker. These are used on system voltages from 230 kV to 550 kV and a current rating of up to 4000 amps. The primary contacts on the circuit breaker need to be separated quickly to clear the fault and ensure that any arc does not restrike. For breakers above 11,000 volts, the separation of the contacts is done using a spring mechanism, which is charged by an AC or DC motor. A spring is used as it provides a large amount of mechanical energy in a short time frame and also allows the mechanism to be operated even after a power failure. The circuit breaker mechanism will normally be designed to have enough stored mechanical energy to allow the breaker to be closed and then opened again, which is needed if the circuit breaker is closed onto a faulted system. Let's look at the key elements of a circuit breaker mechanism. Here's a typical mechanism for a high voltage circuit breaker. First, we have the electrical closing coil for operating the CB remotely. We then have the electrical trip coil for opening the CB remotely. These close and trip coils are basically heavy-duty solenoids, which mechanically force the mechanism to operate. We have the springs to store the mechanical energy for operating the mechanism. We have the spring charging position indicator, which shows whether the springs are charged or not. We have the electrical motor for charging the springs. This can either be an AC motor or a DC motor. We have the counter for measuring the number of operations. This is important information for maintenance. We have the auxiliary switches to signal the circuit breaker position. These are connected to the same shaft that drives the circuit breaker contacts. We have the circuit breaker open or close indicator, which indicates the position of the circuit breaker. And finally, we have the insert for the manual spring charging handle. This is there in case we lose all power to the circuit breaker and need to charge the mechanism manually. The circuit breaker auxiliary switches are physically connected to the breaker mechanism and provide a true representation of its position. There are many types of circuit breaker auxiliary switches. The two main ones are normally open, NO, which will open when the circuit breaker is open, and normally closed, NC, which are closed when the circuit breaker is open. Whenever you see a CB auxiliary switch on a schematic diagram, it will always be shown in its natural position, where the circuit breaker is in the open state. We use CB auxiliary switches in circuit breaker control schemes, protection systems, and interlocking networks. Let's look at the circuit breaker indications first. These are fed from a 110 volt DC supply. As we said previously, the circuit breaker auxiliary switches are shown with the circuit breaker in the open position. Let's now close the MCBs and energize the supply. The auxiliary switches feed power to the lamps. As the breaker is presently open, the off lamp lights. Let's now change the circuit breaker position and see what happens. As soon as the circuit breaker changes its state, the auxiliary switches toggle over, and now the on lamp lights up. Let's now look at the circuit breaker open and close control systems. Circuit breakers come in all shapes and sizes, but the mechanisms that operate them are always controlled by DC operated coils to operate the mechanism and open and close the circuit breaker. We call the open coils trip coils. A circuit breaker can have multiple trip coils, one for each of the trip circuits. Let's look at the circuit breaker closed circuit first. Here we have a positive and negative DC supply with a close coil controlled by a manual push button. We don't want to close the circuit breaker unless the spring is charged, just in case we close the circuit breaker onto a fault. Therefore, let's add a limit switch from the spring mechanism. We also provide what's called an anti-pumping relay, which ensures that if the mechanism doesn't close properly on its first attempt, it doesn't keep on trying, which may damage the main contacts as the electrical supply is disrupted. We don't want to try and close the circuit breaker if it's already in the closed position, so let's add some auxiliary switches into the circuit which prevent that. Let's now push the push button. If all three contacts are now in the right position, the circuit breaker will now close. As the system voltage increases, we need multiple ways of operating the circuit breaker. These include the push button on the circuit breaker panel that we saw on the previous circuit, a local control switch on the protection panel, which is in the control room. We also need remote control via SCADA, so the breaker can be operated from the central control system. We also introduce a local remote switch, which allows the person in the substation control room to block control from the remote control room. Let's add these controls into the circuit. So now we have three levels of control. The push button, mounted on the circuit breaker mechanism, or the local control panel. The local close switch, mounted in the control room. And finally, the remote close switch. Let's now push the push button. If all three contacts are now in the right position, the circuit breaker will now close. Let's now reset the system. Let's now operate the local close switch. The breaker now closes. Let's now reset the system. Operate the local remote switch to put it into the remote mode. And operate the remote close. The remote control signal could come from a PC inside the substation or a remote control centre many hundreds of miles from the substation. The trip circuit starts off in a similar way to the open circuit. So we have our local push button, a local open and a remote open. The main difference is we now have additional protection trips operating the trip coil. These are initiated when something goes wrong with the system and the protection systems detect a fault. Let's now operate one of the protection contacts and see what happens. As soon as the contact closes, the trip coil operates and the circuit breaker opens. For single-phase circuit breakers, we simply duplicate all of the push button, switch and relay contacts and feed them separately into each of the phase mechanisms. Keeping the three-phase trip and close circuits electrically separate allows us to trip and close the circuit breaker phases individually. This feature is required for some H3 networks. single-phase tripping closing is used on extra high voltage systems above 400,000 volts, where the number of customers affected by a disruption can be significant. If a single-phase fault occurs on, say, the red phase, we trip the red phase circuit breaker only and keep the yellow and blue phases connected to maintain the supply. For certain transient types of faults, for example where a tree has touched an overhead line, we then try and reclose the red phase circuit breaker and restore all three phases. Let's summarize what we've learned today. Circuit breaker mechanisms are complex devices that allow the contacts to be closed and opened quickly. The circuit breaker auxiliary switches indicate whether the circuit breaker is in the open or closed position. The close and trip circuits are fed from a DC supply and are controlled from various sources, including control switches and protection contacts. Congratulations for completing this module. You should now understand how important circuit breakers are to our protection system and have a practical knowledge of how they operate. I've attached some questions on today's module to test your knowledge. Welcome to the first module on overcurrent protection. Overcurrent protection is the most widely used protection device that we use on the distribution and transmission network and appears on the most simple and complicated system. In this module, you will learn the basic principles behind instantaneous overcurrent protection and see how an overcurrent relay is connected to the current transformers that feed it. The aims of the course today are to show the fundamental principles behind overcurrent protection, to show how to connect an overcurrent relay to current transformers, to show how an overcurrent relay can be used to detect an overload situation and a fault. Overcurrent relays are used widely in substation protection systems. They are used to monitor the current levels and to operate when the level exceeds a certain amount. These are the symbols for an instantaneous overcurrent relay. We have the ANSI symbol and the IEC symbol. Instantaneous overcurrent relays are usually set to operate just higher than the current capacity of the circuit that they are protecting. Here we have a typical feeder with a circuit breaker rated at 1600 amps and a 1600 to 5 CT. As usual, P1 faces the circuit breaker. For the circuit shown, which is rated at 1600 amps, it would make sense to operate the overcurrent relay when the current goes 10% above the circuit rating. Therefore, relay operating current I0 equals 1.1 times by the CT nominal current IN. This equals 1.1 times by 1600 amps, which is the CT nominal current, equals 1760 amps on the primary side. We have a 1600 to 5 CT. Therefore, the secondary current equals 1760 multiplied by the inverse of the CT ratio, which is 5 divided by 1600. This equals 5.5 amps. Obviously, most of the time the circuit is healthy, and the overcurrent relay sits there monitoring the currents. Here's our feeder from before. Let's set the overcurrent relay to 1.1. Let's now close the circuit breaker. The current on the feeder will now increase. The amount of current depends on the type of load connected to the feeder. Let's now increase the load and see what happens. The load current has exceeded the 1.1 IO setting for the overcurrent relay. It picks up and instantaneously trips the circuit breaker, disconnecting the load. The overcurrent relay is therefore providing a basic overload function to protect the bus bars and circuit breaker from damage. Most overcurrent relays combine all three phase overcurrent elements. Let's see how the CTs are normally connected. Firstly, we have a red phase 1200 to 1 CT. We have a yellow phase CT and a blue phase CT. The red, yellow and blue phase inputs are now fed into separate phase elements inside the overcurrent relay. The three neutral connections are now summated together and fed into the relay. The CTs are grounded at one common point via one grounding link, which is located in the relay panel. Let's now apply load to all three phases and see what happens. Each individual phase element inside the overcurrent relay will now measure its own phase current. Let's now simulate something going wrong on the red phase. The current on the red phase will now increase beyond the 1.1 IN level. The red element will pick up, and the relay will send a trip signal to the circuit breaker. The overcurrent relay is now being used to detect faults on the system. All three phase elements can be set to operate at a different pickup value, IO, but are normally set at the same value, which is just above the current rating of the equipment being protected. The overcurrent phase element can be arranged to trip all three phases of the circuit breaker if a fault appears on any of the three phases. Or, where we have single-phase circuit breakers, for example in transmission systems, we can trip them individually. Let's now look at a more complex scenario. Here's a typical distribution network, with a 1600 amp incomer feeding a bus bar, which then feeds some 800 amp feeders. As per the previous slide, let's set all of the overcurrent relays to 1.1 times by their circuit rating. For the incomer, the relay will operate at 1760 amps, which is 1.1 times by 1600 amps, which is the circuit rating. For the feeders, the relays will operate at 880 amps, which is 1.1 times by their circuit rating. Let's now close the circuit breaker. Let's now apply a fault on one of the feeders and see what happens. As you would expect, the current increases on the main incomer as the source starts feeding the fault. As most systems are fully interconnected, you will also get some current feeding back through the feeders. All of the relays will detect the overcurrent and will pick up, shown by the green LEDs. As the current level will rise on all of the circuits beyond the 1.1 operating threshold, all of the circuit breakers will trip for a fault on any feeder, whilst what we want to do is trip only the feeder that is faulty. Therefore, we need to add some additional features into our relays to improve the fault discrimination. Instantaneous overcurrent protection is the main feeder protection on distribution systems from 11 kV up to 66 kV and is used as a backup protection for transmission systems. It is a very reliable and simple protection, as you know that if the current goes above a certain level, something has gone wrong with the electrical system and you have to trip the circuit breaker. The main issue with instantaneous overcurrent protection is that all feeders that see an overcurrent will trip. So if you get a fault, you will lose substantial parts of the network, and we therefore have poor fault discrimination. Let's summarize what we've learned today. Overcurrent relays can be used to protect the primary system from overload. Three-phase overcurrent relays can detect a fault on any individual phase. Instantaneous overcurrent relays are sufficient for simple systems, but do not provide great fault discrimination. Well done for completing this module. You should now understand all of the fundamental principles behind instantaneous overcurrent protection and why it is so key to our protection system. This knowledge will help you with the next section, which looks at other features we can add to the overcurrent relay to improve the fault discrimination. I've attached some questions on this module to test your knowledge. This is the second module on one of the most important protection relays that we use on the network, overcurrent protection. We will introduce you to some additional features that will improve how the relay reacts to faults and provide better fault discrimination to keep as many of the customers connected as possible when something goes wrong with the network. The aims of the course today are to introduce the principles of overcurrent time grading and see how we can use it to achieve fault discrimination, to introduce the principles behind directional overcurrent relays, to show how the voltage that is applied to directional overcurrent relays affects their performance, one simple thing we can do is to add a time delay before the overcurrent relay trips its circuit breaker. Let's see how that might work. Here's our circuit from before. Let's do the settings now. For the incomer, the relay will operate at 1760 amps at before. But this time, for the incomer circuit breaker, let's also add a time delay of 0.5 seconds. For the feeders, the relays will still operate at 880 amps. The feeder relays will have no time delay. Let's now close the circuit breaker. Let's now apply a fault. The relays will all detect the currents as before, and the overcurrent elements will all still pick up, shown by the green LEDs. The feeder breaker will now operate first, clearing the fault before the time delay on the incomer breaker runs out. But the feeder breakers all trip together, as they are all set to the same time delay, as we have to treat them all the same, as we don't know which one's going to go faulty. Therefore, we still have poor fault discrimination. Another feature we could introduce is to vary the time delay on the overcurrent relay as the current level changes. It is our aim to operate the circuit breaker that are closest to the fault first to provide good discrimination. As the current level increases, the operating time of the relay should decrease, as shown on this graph. To allow this to happen in a defined way, a series of curves have been developed. Let's look at some of the curves. Here we have a graph, with the relay operating time in seconds on the left-hand side. On the bottom axis, we have the current, which is multiples of the CT secondary current IS. The graph is logarithmic, which means each section is 10 times the value of the previous one. We need a logarithmic graph, as the secondary current can span a huge range, from 1 to 100 amps. The first curve is called a standard inverse, or SI curve. As the current increases, the relay operating time decreases. If we pick a point on the standard inverse curve, we can see that for low current levels, the operating time of the relay is high. For a higher current, the operating time drops substantially. When the current reaches a certain level, the curve flattens out, and the operating time remains constant. This is to deal with serious, high-level faults that occur. There are several other curves available. These are the most common. Firstly, we have the definite time, or DT curve. For this curve, the operating time is constant across the full current range. We then have the very inverse, or VI curve, and the extremely inverse, EI curve. It is useful to have a suite of curves available so that we can ensure good fault discrimination in all system configurations. The shape of the curves are defined in IEC standards. This is just a sample of the curves available. Modern numerical feeder protection relays contain hundreds of curves and variants, with multiple current detectors which can all operate in parallel. On older substations, you will come across overcurrent relays with a round metal disc. These are called induction disc relays. In these devices, the curves shown here are achieved using electromagnetism. A coil fed from the current transformer induces a magnetic field onto the metal disc, which then spins and operates the trip contacts when a certain level of current is achieved. The higher the level of the current, the faster the disc spins and the lower operating time. The other way to provide good fault discrimination is to measure the direction of the current. We do this using directional overcurrent relays. Here are the standard symbols for a directional overcurrent relay. Firstly, we have the ANSI symbol and the IC symbol. For an overcurrent relay to calculate the direction of the current, it needs to measure the voltage as well. This is done via a connection to the system voltage transformer. Here we have the typical feeder circuit from before. This time we've connected a voltage transformer to the relay, with a ratio of 11,000 volts to 230 volts. Different utilities have different standards, but it is common to set current flowing from P1 to P2 as forward current, and current flowing from P2 to P1 as reverse current. Let's now set our directional relay to 1.2 for the current pickup, and to operate in the forward direction only. Let's now close the circuit breaker. Let's now apply fault on the feeder. As we can see, the relay trips the circuit breaker instantaneously at 1920 amps. Let's now reset the circuit breaker. Let's now apply a fault to the bus bar. The current pickup has come in at 1920 amps, but as the current is in the reverse direction, the relay does not operate. When using directional overcurrent relays, we need to think about the voltages and currents that we're using to feed the information into the relay, as they will have an effect on how the relay views any fault. Here are the options for the current and voltage connections. Firstly, we have what's called a 90-degree connection, where we apply the red, yellow and blue currents as normal, but the line voltage applied comes from one of these three sources. Next we have the 60-degree connection, which has these line voltages applied. And finally, the 30-degree connection, which has these line voltages applied. The option of whether it's a 90-degree, 60-degree or 30-degree connection can be set inside the directional overcurrent relay. Once we know the voltage and current connection type, we can set up the relay to either operate or restrain for the direction that we want to detect. Here we have a graph with the current on the vertical and the voltage on the horizontal. We draw two lines, the maximum torque line and the zero torque line, with the operate zone on the right of the zero torque line and the restrain zone on the left of the zero torque line. The maximum torque angle, MTA, is defined as the angle by which the current applied to the relay must be displaced to provide maximum torque. We will look at MTAs for different circuit types and voltage inputs in the future protection settings course. Don't worry about this graph too much. Things will become much clearer when we do the protection settings course and see how to use the maximum torque angles to operate the relay in the right direction. The main lesson to learn here is that when we are using directional overcurrent relays, we need to know how the voltage that is fed into the relay is derived, as it will affect how the relay detects which direction the current is flowing. An interesting point is why we are talking about torque when dealing with directional overcurrent relays. This goes back to the induction disk relays that we looked at a couple of slides ago. The torque, or spinning force on the disk, dictated whether the relay operated or not, and is why this term is used. Let's summarize what we've learned today. Time and current curves and directional elements are used to provide better fault discrimination for overcurrent relays. We need to select the right overcurrent relay for the correct location to provide a fully operational system. When using directional overcurrent relays, the source of the voltage applied can affect how the directional overcurrent relay sees the fault. Congratulations for completing this module. You should now understand all of the features of an overcurrent relay. In the next module, we will see how these features can be applied to some real networks and start to understand how powerful an overcurrent relay can be in keeping the network safe. I've attached some questions on today's module to test your knowledge. In this module, we will introduce some practical examples of how to use all of the available features of overcurrent relays. It is obviously impossible to cover every single network configuration, but hopefully, by the end of this section, you will have learned some basic principles that can be applied to any situation. The aims of the course are to show how overcurrent time grading and directional elements can be used in various network configurations. Let's now use our curves and direction elements in the network from before. For the incomer, the relay pickup is set at 1.1, which is 1760 amps on the primary. The directional element is set to forward. The curve we choose is standard inverse. For the feeders, the relay pickup is also set at 1.1, which gives a current on the primary of 880 amps. The directional element is set to forward. The curve we choose is standard inverse. Let's now close all of the circuit breakers. Let's now apply a fault on one of the feeders and see what happens. As before, the current will increase on the incomer and all of the feeders, and the overcurrents all pick up. But the only circuit breaker that trips is on the faulty feeder. Let's see why. On the incomer, the overcurrent relay detected the fault and it was in the right direction. But because of the standard inverse curve, there was a slight time delay, which allowed the faulted feeder to trip first. For feeders C, D and E, again they all saw the current and the overcurrent relays picked up. But the current that they see is in the reverse direction. Therefore, the relays don't operate. By using the directional elements and the curves, we've now achieved good fault discrimination, because only the breaker on the faulted feeder has tripped. Let's do a worked example. For the overcurrent relays on ends A, B, C and D, decide on the current pickup setting, the curve to use, and whether the relays will operate in the forward or reverse direction to deal with fault number 1. The aim is to clear the fault and keep the other feeder supplying the load. Here's the proposed solution. For the relays on ends A and B, let's make the current pickup 1.2, which is 960 amps on the primary. Let's have a definite time delay of 0.5 seconds, and the current direction as forward. For the relays on ends C and D, let's make the current pickup as 1.1, which is 880 amps on the primary. Let's have a time delay of 0 with no curve, and the current direction as forward. Let's now close the circuit breaker. Current will now flow from the power source through feeder 1 and feeder 2 onto the load. If the two feeders are the same length, the currents should be shared fairly equally. Let's now apply a fault on the feeder from A to C and see what happens. The currents will increase substantially on both feeders, with additional current backfeeding from end D to C. Let's now see how all the relays react. All 4 relays saw an increase in current and therefore picked up. A and B will see current in the forward direction. End C will also see current in the forward direction due to the backfeed from feeder 2. End D will see current in the reverse direction. The first relay to trip will be on end C. There's no time delay and the direction is forward, which is correct. This will then remove the backfeed from feeder 2, and the currents on ends B and D will now reduce below the pickup level. Feeder 2 can now carry on feeding the load. The current on end A still remains high, as it's still feeding the fault. After the time delay of 0.5 seconds, end A will now trip, clearing the fault. For the overcurrent relays shown, decide on the current pickup setting, the curve to use, and whether the relays will operate in the forward or reverse direction to deal with a fault in any of the locations shown. The aim is to clear the fault quickly and keep the load supplied. This arrangement is a typical ring system used on a distribution network. Let's now see the best solution. This is a very complex network, and the best way to deal with it is to split it into two separate networks. Here's the first network. Firstly, let's set all the relay pickups to 1.1 as usual. Let's set all the direction elements to the same direction, with all the directional elements indicating current flowing away from the power source. We want the relay farthest away from the power source to have the shortest duration, so let's give it a delay of 0.2 seconds. As the relays get closer to the power source, the time delay should increase. So let's add a time increment of 0.4 seconds for each of the relays as they step towards the power source. Let's now apply the same principle to the second chain. Let's now transfer these time delays and current directions onto the original network. We end up with this arrangement, with all the relays on the left of the breakers looking left, and all the relays on the right of the breakers looking right. Let's now close the circuit breakers. As we can see, the main currents from the power source will split, with some going down the left-hand side and some going down the right-hand side. How these currents split will depend on the value of each of the loads applied. Let's now apply fault at position 1. As we can see, straight away, the currents change direction to feed the fault. The currents will now increase substantially on both legs, and all of the overcurrent relays in the chain will detect the increase in current and pick up. What comes into play now is the direction of the currents and the time delays. As we can observe, the overcurrent relay associated with circuit breaker C sees the fault in the correct direction and has the lowest time delay and operates first. This disconnects the fault from the right-hand side of the chain. On the left-hand side of the chain, the only overcurrent relay that sees the current in the correct direction is now on circuit breaker B. This trips after 1.4 seconds, clearing the fault. Let's now remove the fault and reset the circuit breakers. Let's now apply fault number 2. Again, the currents change direction to feed the fault. The currents will now increase substantially on both legs, and all of the overcurrent relays in the chain will detect the increase in current and pick up. This time, the overcurrent relay that reacts first is on circuit breaker F, removing the fault from the left-hand ring, and fault current is now supplied from the right-hand side of the network. The only relay that now has current flowing in the correct direction is now on circuit breaker G. This trips the circuit breaker, isolating the fault. We obviously can't look at every network configuration possible, but you should now see how the time current grading and directional elements of an overcurrent relay allow us to provide good fault discrimination for most types of networks. The main issue with using overcurrent relays is the time that we sacrifice to achieve this level of fault discrimination. In some of the networks we've just looked at, it's taken up to 1.4 seconds to clear the fault. This delay may be acceptable for some distribution networks, but if we try to hold off for this long on a transmission network, the high level of fault current would critically damage the equipment and probably cause a system-wide collapse. In the future Advanced Protection System course, we will look at some different types of protection that combine an ability to provide good fault discrimination, but do it in a reduced clearance time. Let's summarize what we've learned today. Time and current curves and directional overcurrent elements can be used to provide good fault discrimination for most types of networks. Congratulations for completing this module. You should now understand all about overcurrent relays and be able to configure them for use on any type of network that you may come across. In the final section, we will look at the sister relay of overcurrent protection, namely the earth fault relay. I've attached some questions on today's module to test your knowledge. Congratulations for making it to the final module, which covers earth fault protection. Earth fault protection operates in a similar manner to overcurrent protection, so the principles behind this course should be easy for you to understand. Although the specific ways in which we connect earth fault relays to the current transformers needs to be fully understood to make the principles clear. The aims of the course today are to show the fundamental principles behind earth fault relays and show how they can be connected, to introduce the different types of earth fault relays that we use on the network, to show how earth fault relay elements are combined with overcurrent elements, earth fault relays are used widely in substation protection systems. They are used to monitor the currents that can happen when an earth fault occurs on the system, and to operate when the level exceeds a certain amount. These are the symbols for an instantaneous earth fault relay. Here's the ANSI symbol, and here's the IC symbol. Earth fault relays need to be connected so that they measure the CT spill currents that occur when an earth fault occurs on the system. In a three-phase system without a neutral, we simply connect the red, yellow, and blue phase current transformers in parallel and connect them to an earth fault relay. Each CT will generate its own current, so we have red phase current, yellow phase current, and blue phase current. If there is no earth fault present, the vectors will always cancel each other out. No current flows into the earth fault relay, and it does not operate. This type of connection is called a balanced earth fault arrangement. If we are protecting a three-phase system with a neutral, for example a distribution system, we simply monitor that as well. The current flowing back through the neutral wire will range from 0 in a balanced three-phase system through to the maximum phase current when only one phase is loaded. The summation of the full elements will always equal 0, unless an earth fault occurs. For this arrangement, it is obviously essential that all of the CTs have the same characteristics. Otherwise a spill current will be created, which may be enough to operate the earth fault relay. At lower voltage systems, a toroidal coil can be provided, which goes over the phases in neutral, and will only provide a spill current when an earth fault occurs. In most applications, the earth fault feature is combined with the overcurrent elements to provide a multi-function relay. To achieve this, we connect the earth fault element in series with the summated overcurrent elements to create a virtual earth. Let's now look at a transformer. Here we have a typical three-phase transformer with red, yellow, and blue windings. All earth fault currents will flow back to the source of the electrical energy, which in most cases is the star point of the source transformer or generator. To provide a very simple and reliable protection system, we can therefore put a single earth fault relay on the ground connection on the neutral point. This relay detects an earth fault anywhere on the network that's connected to this winding. Some stray ground currents are always present, up to 80 amps for the typical transmission transformer, so we need to set the current level above a certain amount. You will find this simple type of earth fault relay even on the most advanced substation, provided as a last resort protection, normally given a long time delay greater than 1 second, which will allow sufficient time for all other protections to operate first. Let's now add a balanced earth fault relay to the transformer. This is connected in the same way as before. Let's now energize the transformer. With no fault present, all the currents are in balance, and no spill current flows into the earth fault relay. Let's now apply a fault to the red phase conductor. Current will now flow through the red phase, into the ground, up through the ground conductor for the neutral point, and back to the transformer. We can see the current flowing into the ground through the red phase means that the 3 current phases are no longer balanced, and the relay operates. Our balanced earth fault relay will detect an earth fault that appears anywhere on the connected system. Let's see how we can detect an earth fault on the transformer itself. To detect an earth fault on the transformer, we use a zonal or restricted earth fault protection. To make it zonal, we connect the 3-phase CTs to a CT on the ground connection. Let's now energize the transformer. Let's now apply a fault on the red phase outside the zone and see what happens. As expected, we now get additional earth fault current on the red phase. This is now balanced by the current detected by the CT on the ground connection. If a fault occurs outside the defined zone, all of the current still balance, and the relay does not operate. Let's now remove the fault and apply a fault inside the zone on the transformer itself. This time there is no earth fault current generated on any of the phase CTs, but we do have current flowing through the CT on the ground connection. This imbalance will cause a spill current, which is enough to operate the earth fault relay. The CTs used for the restricted earth fault protection will all have slightly different characteristics due to their manufacture. If we have a high current fault outside the zone, these differences can be magnified, which may lead to the earth fault relay tripping inadvertently. To overcome this, we provide a stabilizing resistor in series with a voltage-operated relay. This provides the scheme with a lot more stability. By varying the size of the resistor, we can deal with all types of faults outside the zone. Restricted earth fault protection is provided on most high-voltage transformers, as it gives a clear indication that an earth fault has occurred on the winding being monitored. The stabilizing resistor value depends on the CT resistance and the resistance of the CT wiring. We will see how to calculate this in the future protection settings course. In exactly the same way as the overcurrent relays, we can also use time and current grading to provide better discrimination than our earth fault relays, and all the standard curves and settings are available in most modern relays. We can also provide directional earth fault relays, which give an indication of where in the system the fault has occurred. Here's a typical symbol for a directional earth fault relay. Here's the ANSI symbol and the IC symbol. Let's summarise what we've learned today. A simple earth fault relay can be provided on the transformer neutral as a last resort protection. Earth fault relay elements can be incorporated into overcurrent relays and use the same current transformers. Restricted earth fault relays are used on transformers to detect an earth fault on the transformer itself. Well done for completing the course. Hopefully, you will have learned a lot about the theoretical and practical aspects of electrical protection systems. In the next course, we will use this knowledge to look at some of the more advanced protection systems that you will come across. I hope to see you then.